Vadim Lozin, Warwick, and he will talk about Hamiltonian cycles and classes.
Okay, thank you. Okay. Hi, everybody. First of all, I would like to thank Sangil for the invitation. It's great to be here in the nice city of Daejeon for the second time. For the first time, I've been here in 2011 when I attended the GROW meeting organized again by Sangil. It's a workshop on graph classes, optimization problems, and width parameters. And this is what I do for the last 40 years or so, among other things, of course. I mean, graph classes, graph problems, graph parameters, and this is what I'm going to discuss today. But most part of my talk will be devoted to a specific problem, the Hamiltonian cycle problem. That's why I put a subtitle, the Hamiltonian cycle problem in monotone classes. But first of all, let me formally define the notion of a monotone class. It's a class of graphs closed under taking subgraphs, not necessarily induced, meaning that if you have a graph in your class, you can delete a vertex, you can delete an edge, and the graph remains in the class. Examples of monotone classes are forests, bipartite graphs, subcubic graphs, meaning graphs of degree at most 3, of vertex degree at most 3, planar graphs, or more generally, all minor closed classes of graphs are monotone, including the class of all graphs. So the family of minor closed classes is a proper subfamily of the family of monotone classes, and the family of monotone classes is a proper subfamily of the family of hereditary classes. And since every monotone class is hereditary, it admits a characterization in terms of minimal with respect to the induced subgraph relation graphs, minimal forbidden induced subgraphs. And similarly, every monotone class can be characterized by a set of minimal with respect to the subgraph relation graphs that do not belong to the class. The two sets of forbidden graphs, forbidden subgraphs and forbidden induced subgraphs, they may coincide, they may be different, but what is important for us is that either both of them are finite, in which case we will say that our class is finitely defined, or both of them are infinite. For instance, in the case of forests, the two forbidden sets are coincide. In both cases, I use the word free for the induced subgraph, for forbidden induced subgraphs, and subgraph free for forbidden subgraphs. So in both cases, it's the set of all cycles. The same story for bipartite graphs, where we forbid either as induced subgraphs or as subgraphs all cycles. But for the subcubic graphs, graphs of degree at most 3, the two sets are different. In the case of forbidden subgraphs, we just need to forbid K14, the only minimal graph with a vertex of degree 4. But if we want a forbidden induced subgraph characterization, we have in total 11 forbidden graphs obtained from this one by adding some edges. Okay. So speaking of minor closed classes of graphs, in this family there are classes that play some critical role, and perhaps the most famous example is the class of planar graphs. It is critical in the sense that every minor closed class containing the planar graphs have unbounded tree width, unbounded clique width, and many algorithmic problems, and be complete whenever the class contains all planar graphs, including the independent set problem, the dominating set, Hamiltonian cycle, and many other problems. On the other hand, if you have a minor closed class of graphs excluding at least one planar graph, then the tree width is bounded, clique width is bounded, and many problems become polynomial time solvable, including all three problems listed here. I will give you a couple of more examples of critical classes, trivial examples, but still interesting. let's look at the borderline separating the class of all graphs, which is a minor closed class of graphs, from all proper minor closed classes. We know that any proper minor closed class of graphs is small, whatever it means. It has something to do with the number of graphs in the class. Every proper minor closed class admits an implicit representation and has bounded twin width. But for the class of all graphs, of course, is not small. It does not admit an implicit representation. Twin width is unbounded. Now let's look at the other side of this universe, of this hierarchy. At the bottom of this hierarchy, where we find the class of empty or edgeless graphs. And this class is also critical in the following sense. If you have a minor closed class of graphs containing all empty graphs, then it's infinite. And if you exclude an edgeless graph from a minor closed class, it's finite, because by excluding an empty graph, you also exclude all graphs containing it as a subgraph. So in particular, you exclude the complete graph, and therefore it's a finite class. So in a sense, this class is critical for the very basic parameter, the number of vertices. Any minor closed class containing all edgeless graphs, the number of vertices can be arbitrarily large, and in any minor closed class excluding at least one edgeless graph, the number of vertices is finite. Actually, with any graph parameter, we can associate a number of minimal minor closed classes of graphs where this parameter is unbounded. I don't claim that identifying such minimal classes is an easy task, but what I claim is that such classes necessarily exist in the universe of minor closed classes, because the minor relation is a well quasi-order, and therefore there are no infinite anti-chains of graphs, and as a result there are no infinite strictly decreasing sequences of classes, which is not the case for the universe of monotone classes, where we find, because the subgraph relation is not a well quasi-order, there are infinite anti-chains, and cycles present one of the most simple examples of an infinite anti-chain with respect to the subgraph relation. As a result, we can construct an infinite, strictly decreasing sequence of graph classes, excluding small cycles of length up to k. And with k tending to infinity, this sequence converges to graphs without cycles. And for each class in this sequence, the chromatic number is unbounded, but in the limit class, it is bounded by 2. So in this sequence of graph classes, there is no minimal class of unbounded chromatic number. And a minimal so this is the limit of this sequence, and a minimal limit class is called the boundary class, and the importance of this notion is due to the fact that it plays the role of minimal classes if we talk about finitely defined classes. In particular, with respect to the chromatic number, we can state the following, make the following claim. I found that I have a typo here. You should read unbounded. So the chromatic number is unbounded in a finitely defined class if and only if the class contains a boundary class. And in this terminology, the famous conjecture about chi-bounded classes can be stated in the following way. The class of forest is the only boundary class, meaning that if we exclude a forest, then we obtain a class of bounded chromatic number. a chi-bounded class, more precisely, a chi-bounded class. So the class of complete graphs, it's a minimal class, hereditary class of unbounded chromatic number. The class of forests is a boundary class, but it's only a conjecture. Of course, the conjecture is wide open, but it becomes a valid statement if we restrict ourselves to monotone classes. In the universe of monotone classes, this conjecture becomes a valid statement. Any monotone class excluding a forest, in any monotone class excluding the forest, the chromatic number is bounded. Because the degeneracy is bounded, which is another parameter, and which is not difficult to show. So, on the other hand, if you have a finitely defined class, monotone, which does not exclude a forest, then it necessarily includes a class of this type for a finite value of k, in which case the chromatic number is unbounded. So, in the family, in the universe of monotone classes, the class of forests plays a critical role. It's a critical class. For finitely defined classes, let me emphasize, for finitely defined classes. What other critical classes exist in the universe of monotone classes? When I asked myself this question, I realized that I cannot find any specific reference to any specific result of this type. But some results of this type can be derived, sometimes easily derived, sometimes with some extra work, from known results. So I started collecting this information about critical classes in the universe of monotone classes, and here is the picture which contains all my findings which I have been able to collect so far. So let me briefly discuss this picture. At the bottom of the picture we again see what I call level 0, classes of graphs which are finite. Level 1 contains classes where monotone classes with bounded matching number, vertex cover number, and neighborhood diversity. So any monotone, and the critical class for this level is the class of graphs of degree at most 1. So any monotone class of graphs containing all these graphs has unbounded matching number, unbounded vertex cover number, unbounded neighborhood diversity. On the other hand, if you exclude any graph from this class as a subgraph, then you obtain a monotone class of bounded matching number, vertex cover number, and neighborhood diversity. And this is the only level for which this classification is valid regardless of whether we talk about finitely defined classes or not. It's valid for any classes. All other levels are associated with finitely defined classes. So what's the next level? The next level contains classes, finitely defined monotone classes with bounded path number. I would like to avoid definitions because they are irrelevant here, but I can define these. So with bounded path number, tree depth, and these are classes which are well quasi-ordered under the subgraph relation. And the critical class here, linear forests or path forests. So any finitely defined class containing all linear forests are located above this line, and any finitely defined class, monotone class, excluding at least one linear forest, belong to this level. The next level is the most interesting one, perhaps. It consists of classes, finitely defined classes, monotone classes, where with bounded tree, clique, or twin width, and where many algorithmic problems such as maximum independence set, maximum induced matching, and many other problems are polynomial time solvable. And the critical class here is the class of so-called tripod forests. I call a graph of this form a tree with a single vertex of degree 3 a tripod, and a tripod forest is a forest in which every connected component is a tripod. So any monotone finitely defined class which includes all tripod forests have unbounded tree width, unbounded click width, unbounded twin width, and these problems are NP-complete in such a case. And once you exclude a tripod forest as a subgraph, you have bounded tree width, bounded click width, bounded twin width, and polynomial time solvability of many problems. The last level consists of classes, finitely defined monotone classes, where we have bounded degeneracy, bounded chromatic number, bounded functionality again. It's a certain graph parameter. And classes that admit an implicit representation and have at most factorial speed of growth. And the critical class in this case, the class of all forests. Once you exclude a forest as a subgraph, you find yourself in this level. And any monotone class containing all forests is above this line. And of course, let me state it explicitly that this is just a few first step towards characterizing the universe of monotone class. Of course, many other levels, many other critical classes can be identified by looking or exploring some other graph parameters, graph problems. For instance, let's look at the Hamiltonian cycle problem. Where is it in this picture? It's not listed here. Why? We know that the Hamiltonian cycle problem can be solved in polynomial time on graphs of bounded tree width. So it should be maybe somewhere here.
Mm-hmm.
But on the other hand, there are monotone classes of unbounded tree width. And we will see an example in a few minutes where the Hamiltonian cycle problem still admits a polynomial time solution. So it should be strictly above this line. And on the other hand, if we do not exclude the forest as a subgraph in a finitely defined class, then the problem is NP-complete. Again, we will see this in a few minutes. So it's somehow in between these two levels. And I have no idea how the critical classes look like for this problem. So let's look at this problem in more detail to better understand the critical classes for this problem. The Hamiltonian cycle problem. You know, it's a cycle is Hamiltonian if it contains all vertices of the graph. The problem is NP-complete in general and is solvable in polynomial time for graphs of bounded tree width. And in terms of boundary classes, we can say that any algorithmic problem, including this one, is NP-complete in a finitely defined class if and only if this class contains at least one boundary class for our problem. And the first boundary class for this problem was identified in this paper in 2011, published in 2011. And to define this class, let me first introduce the notion of a caterpillar with hairs of arbitrary length. This is a subcubic tree in which all cubic vertices belong to the same path. I represent this path horizontally, and the paths represented vertically, I will refer to them as hairs. And the boundary class is the class of graphs where every connected component has this form. So I will throughout this talk I will denote it by phi. So what we proved is that the class phi of graphs, every connected component of which is a caterpillar with hairs of arbitrary length, is a boundary class for the Hamiltonian cycle problem. Which means that the Hamiltonian cycle problem is polynomial time solvable in a finitely defined class only if our class excludes a graph from this class. It's a necessary condition, but not sufficient, as we shall see in a few minutes. Now, let's look at what can happen if we exclude a graph from this class. Let's exclude a tripod forest, which is a graph from this class, of course, just one hair. Then we have bounded tree width, and the problem is polynomial time solvable. A result obtained for free. Okay. What we exclude a graph with two hairs, consecutive. which are consecutive on this path. So this is what I denote by F2, but in general, Fk is the graph of this type with 4 branches of length k. And I claim that by forbidding this graph, we obtain a class where the problem admits a polynomial time solution. The proof is nice, I think, and short, so I decided to present the whole proof. But for this I need some terminology. So assuming that our graph contains a Hamiltonian cycle, I will call any edge which does not belong to the cycle a chord. A chord splits the cycle into 2 paths, and the length of the shortest of them, I will refer to it as the length of the chord. Now, assume we have a graph G, which is Fk subgraph 3. K is a fixed number. And assume that our graph has a Hamiltonian cycle. Then every chord has length at most 2k, because if both paths are sufficiently large, then we find immediately a forbidden graph. So if our input graph has a Hamiltonian cycle, then the length of any chord is at most 2k, which implies that the tree width of G is at most 4k, which is not difficult to show. Which means that if our input graph has tree width more than 4k, which can be checked for a fixed value of k in linear time, then it has no Hamiltonian cycle. And if the tree width is bounded by 4k, there is an algorithm to decide whether it contains or does not contain the Hamiltonian cycle. So an easy and nice argument shows that by forbidding an Fk as a subgraph, we obtain a class which admits a polynomial time solution for this problem. But what if we forbid a graph with 2 hairs which are not consecutive, like here? Everything becomes much more complicated. I denote this graph shown here by H2. In general, by HK, I denote a graph of this form. It's a tree with 2 vertices of degree 3 connected by a path of length k, HK. So we just proved that for H1, which is the capital letter H, the problem admits a polynomial time solution. What about H2 subgraph free graphs? I will show you that for some values of k, the problem is polynomial time solvable. For some of them, it's NP-complete. But before that, let me make a short detour in the area of well quasi-ordering. This detour is irrelevant for the rest of the talk, but I think it's interesting, and somehow it justifies the importance of the H graphs. So we know that cycles form an infinite anti-chain with respect to the subgraph relation. The same is true for the H graphs. It's not difficult to see that they are incomparable as subgraphs. None of them can be obtained from the other by deleting vertices or edges. And moreover, together, they form an infinite anti-chain. And this anti-chain of cycles and the H graphs, in a sense, is unique anti-chain for the subgraph relation, which was proved by Warwick in 1992. So what he proved is stated in this theorem. A monotone class is well quasi-ordered by the subgraph relation if and only if it contains finitely many cycles and finitely many H graphs. So if a monotone class contains infinitely many graphs from this anti-chain, then it's not well quasi-ordered. If it contains finitely many graphs from this particular anti-chain, it's well quasi-ordered. Which later, Warwick called anti-chains of this type canonical anti-chains. and proved in particular in this paper that the induced subgraph relation does not contain canonical anti-chains in general. With some restrictions we can find canonical anti-chains, but in general canonical anti-chains do not exist for the induced subgraph relation. By the way, Gualedin contributed to the area of well quasi-order in various ways. In particular, in this paper, chordal graphs, interval graphs, and well quasi-order, he proved that he studied the induced minor relation. It's another partial order graphs, and he proved that interval graphs are not well quasi-ordered under the induced minor relation. So he found an infinite anti-chain of graphs which, with respect to the induced minor relation. And I have a conjecture, which I believe is interesting, stating that if we restrict ourselves to unit interval graphs, then this class will be well quasi-ordered with respect to the minor relation. I have some motivation supporting this conjecture, so if you are interested, I am happy to discuss it. By the way, if you look at the construction of anti-chain for the induced minor relation presented in this paper, you will see that inside this construction, encoded in some clever way, you find the H graphs. And the same story actually happens in some other publications. For instance, this small paper, 4 pages only, which present the only result in this paper, an infinite anti-chain of permutations. If you translate this result to the language of graph theory, permutation graphs, then it will be the complement of an H graph. So this anti-chain consists of the complements of H graphs and the complements of permutation graphs and permutation graphs. And even more recently, just 1 month ago, another interesting paper appeared. And an anti-chain of monomial ideals in a twisted commutative algebra. And the author found an infinite anti-chain. In doing so, he establishes a connection to well-studied posets of graphs under the subgraph and the induced subgraph relation. And if you look at the pictures, you will find the H graphs. The H graphs. And just to finish with this detour, let me observe that I defined the H graphs starting with H1, but we can also define H0 by contracting this H, which is still an anti-chain, an infinite anti-chain. And what happens if we forbid graphs in this anti-chain? We obtain a class of graphs, hereditary and actually monotone. It's the same. I mean, it doesn't matter whether we forbid these graphs as subgraphs or induced subgraphs. We obtain a class of graphs. Can you guess what it is? What is the class of graphs obtained by forbidding all these graphs? Of course, it's a subclass of forest because all cycles are already forbidden. It's the class of tripod forests, which is an important class, important critical class, and again, somehow this justifies, this is precisely the class of tripod forests obtained by forbidding all these graphs. So this somehow justifies the importance of H graphs. Now, let's get back to the Hamiltonian cycle problem and discuss the problem in classes where we forbid HKs for some values of Ks. The Hamiltonian cycle problem is polynomial time solvable for HI subgraph free graphs with I equal 1, 2, and 3. And it is NP complete for HI subgraph free graphs with I greater than 6, greater or equal to 6. For the NP completeness part of this result, I can refer you to this paper where the author studies the problem on directed graphs. In these graphs, each vertex, for each vertex, there is either exactly one edge coming to the vertex and exactly 2 edges leaving the vertex, or we have exactly two directed edges coming to the vertex and exactly one edge leaving the vertex. Only two types of vertices. And he proved that the problem is NP-complete for graphs of this type. Since this is the only edge coming to the vertex, and we are talking about directed Hamiltonian cycles, we know that this edge belongs to any Hamiltonian cycle if the graph contains it. And similarly for this edge is mandatory and this edge is mandatory. And actually we use this result in the paper I mentioned where we described the first boundary class. We use this result. And in the same paper we showed how to translate the problem from directed graphs to undirected graphs. This can be done by omitting orientations and by introducing a vertex of degree 2 on each mandatory edge. The role of this vertex of degree 2 to make these two edges mandatory. So in general, I call vertices of degree 2 white vertices, and vertices of degree more than 3 or more black vertices. We can assume that our graphs do not contain vertices of degree 1 or 0, because we know that Hamiltonian cycles do not exist in such graphs. A black subgraph is a subgraph of the input graph induced by black vertices. And a black component is a connected component of the black subgraph. A white path is an induced path, all vertices of which are white, except the endpoints. So, general structure of graphs in this terminology is this, with respect to these colors, can be described in the following way. We have a number of black connected components, might be just one of them. But if we have several black components, then they are connected to each other by white paths. And actually, each black vertex is incident to at most one. We can assume that each black vertex is incident to at most one white path, because if we have a black vertex, I'm not sure which of them is black, which is white. Yeah. This is black. Okay. This is white. If a black vertex is incident to at least 3 white vertices, then we know that this edge is mandatory, this edge is mandatory, this edge is mandatory. No way to find the Hamiltonians. Okay, so having introduced this terminology, let me now define a notion which I believe is important in this area, the notion of an even graph. It's a connected graph in which every black component is an even induced cycle, and every black vertex is incident to exactly one white path. And we have a small example. One black component, one more black component, one more black component, and they are connected to each other with white paths. What is interesting about even graphs? If an even graph contains a Hamiltonian cycle, we know that this Hamiltonian cycle contains exactly 1/2 of the edges in each black component. And this half of edges creates a matching in this black component. And a black component has exactly 2 matchings, each black component. So all we need to do is just to choose in each black component one of the 2 matchings for the inclusion in the solution. And we want the solution to be connected. That's all we need to make a connected solution. And you can guess that in general this is an NP-complete problem if we have no restrictions. Moreover, I can prove that the problem is NP-complete with the restriction which I call sigma A, where sigma P denotes the class of even graphs in which black components have a length at most P. This conclusion can be derived with some extra work from this result. Actually, if you look at this result, you will and translate this result to the language of undirected graphs, then you will see that it's an even graph. But not necessarily, P is not necessarily 8 at this step, it's a bit higher, but you can easily reduce it to sigma 8. So in this case, the problem is NP-complete. And this implies almost immediately that the problem is NP-complete for HI subgraphic graphs with I greater than or equal to 6. Why this is so? This is because we can assume, fix an I, let's say 6. We can assume that every y path has length more than 6. Because it's, if you have a short y path, add more vertices. You change nothing. You should either include all edges of the path or, not all. You should include all the edges of the path, and the length of a y path is irrelevant. So we may assume that the length is greater than 6. What does it mean? It means that if we want to embed H6 into an even graph, then the two vertices of degree 3 of HI must belong to the same black component, because vertices in different black components are far away from each other. But if we restrict ourselves to sigma 8, you cannot accommodate H6, all vertices of H6. 1, 2, 3, 4, 5, 6, 7, 8. So this is our black component. If we put one vertex of degree 3 of H6 here, then 1, 2, 3, 4, 5, 6. The other should go here. But then this vertex will share two vertices of H6, which is not possible. So this is our H6, and this vertex, we map two vertices of H6 to the same vertex, which is not possible. So we obtain almost immediately that the problem is NP-complete. What about sigma 4, where all black components have size 4? In this case, the problem is easy, even trivial, because all graphs in this class contain a Hamiltonian cycle, and I will discuss it in the very end of my talk. Which implies, not immediately, that the problem is polynomial time solvable for H2 and H3 subgraphic graphs. This is not immediate at all. There is a long sequence of reductions, reducing the input graph to a graph in sigma 4. In this sequence of reductions, you either make conclusion that a Hamiltonian cycle in your graph does not exist, or eventually you reduce the problem to a graph in the class sigma 4. Okay, what about sigma 6? Oh, and this is the most intriguing question in this area, in my view. We discussed already with some people complexity of this problem, but it's open. We don't know what's the answer. But let's discuss the polynomial time solution for H2 and H3. Oh, now before that, I would like to make a couple of more remarks about the complexity of the problem. We know that phi is a boundary class. We know that we must exclude a graph from this class to obtain a polynomial time solution if we deal with finitely defined classes. But it's not the only boundary class. In the same paper I mentioned before, we identified one more class which can be obtained by applying this simple transformation. If you have a cubic vertex and transform the graph in the way shown in this picture, and it's not difficult to see that if the original graph has a Hamiltonian cycle, then the new one has a Hamiltonian cycle, and vice versa. If the Hamiltonian cycle in the original graph uses these two edges, then in the new graph you use these edges, and so on. So the class of graphs, which I denote here by phi triangle of graphs obtained from graphs in phi by replacing each cubic vertex with a triangle, also is a boundary class. It's not a monotone class. Phi is monotone, but phi triangle is not monotone. But it doesn't matter. The theory of boundary classes was developed for hereditary classes, and if we want a polynomial time solution in a finitely defined class, we must destroy each boundary class by forbidding at least one graph from each boundary class. Which implies, in particular, that if we forbid this guy as a subgraph, or this guy as a subgraph, the problem remains incomplete. This guy belongs to phi, this guy belongs to phi, but we cannot obtain a graph from phi triangle by adding edges to this graph. We need to obtain something like this. We need to embed this graph as a subgraph into something like this. And this is not possible. You cannot add edges to this graph because if you add, let's say, this edge, this vertex becomes obliquely full. If you erase this edge, for instance, then you can embed here. You can add an edge here, and you have a graph from this class. So this, by forbidding this graph, we do not destroy phi triangle. Or by forbidding this graph, we do not destroy phi triangle. So by forbidding any of them, we obtain a class where the problem is NP-complete. And an interesting consequence of this conclusion is that if we forbid a graph, in this corollary we deal with just one forbidden graph. If we forbid a graph in phi with at least 5 hairs, then the problem is NP-complete. Because if you have 5 or more hairs, either you find 2 hairs which are far away from each other, in which case hi with a large value of I appears, or you find one of these. And this is not the end of the NP-completeness. Notice that in this construction, every cubic vertex is adjacent, has a non-cubic neighbor. In this case, we can apply a modification of triangle insertion. This is what I call replacement of a cubic vertex with a square. This is a C4, not necessarily a square, a C4. And under the assumption that this edge is mandatory, it belongs to any Hamiltonian cycle, we can conclude that with this transformation, we transform a graph containing a Hamiltonian cycle to a graph containing a Hamiltonian cycle, and vice versa. So this is more or less one more boundary class. It's a class of graphs of this form and all their induced subgraphs, which allows us to make one more conclusion. You can embed this guy into phi triangle by adding, for instance, this edge, and this edge. But you cannot embed this into this construction as a subgraph. That's why by forbidding this graph, we obtain an NP-complete, a class where the problem is NP-complete. Okay. Now let me make before I present polynomial time results, let me make a short summary. So we know that the problem is NP-complete if we forbid HK for k greater than or equal to 6. It is NP-complete if we forbid this guy, or this guy. It's polynomial time solvable for Fk, where we have 2 consecutive hairs. And 2 more results I have been able to obtain so far. But if we forbid this graph or this graph as a subgraph, then we have a class where the problem embeds a polynomial time solution. Each of them contains an H2. This contains an H2, this contains an H2, but this also contains H3 if we delete this here, and actually H1. So by proving that by forbidding this graph, we obtain a class with polynomial time solvable Hamiltonian cycle problem. We prove that the problem is polynomial time solvable for H1, H2, and H3 subgraph free graphs. Let me sketch the proof of this result. Once again, T is the graph represented here. Just you remember it, the graph. So we can start with some easy observations. If the graph has vertices of degree 0 or 1, then it has no Hamiltonian cycle. If the graph is disconnected, it has no Hamiltonian cycle. If a graph contains a vertex adjacent to more than 2 white vertices, it has no Hamiltonian cycle. And if the graph contains a vertex V adjacent to exactly 2 white vertices, then we can delete all other vertices, except the 2. Then we can delete all other edges connecting V to the white neighbors. We can delete all edges except those that connect this vertex to the white neighbors, because we know that the 2 edges are mandatory, and the other edges will not be used in any Hamiltonian cycle. And by deleting an edge from a graph monotone class, we obtain a graph in the same class. Then perhaps I will skip some other reductions up to this point where we conclude that we reduce the graph to the form where every connected component has a bounded size. Every black component has a bounded size. Size of this many vertices. Okay, so now we know that if our input graph has a black component with many vertices, more than this amount, we know that the Hamiltonian cycle does not exist. What if it has at most a bounded number of vertices in each black component? Assume such a graph contains a Hamiltonian cycle. And on this, and we may assume that the graph is large enough, because otherwise we can solve the problem by brute force. Then on a Hamiltonian cycle, black vertices alternate with white vertices. I call a sequence of black vertices at a black interval, and each black interval consists of at least 2 vertices. Because if it's a single black vertex, then we delete all other edges and make it white. Yeah. The black vertices that have white neighbors, I call them contact vertices. This vertex has a white neighbor, this vertex has a white neighbor. These also are contact vertices. Each interval gives rise to exactly 2 contact vertices. So therefore the number of contact vertices must be even in any black component, which means that if in your input graph you have a connected component with an odd number of contact vertices, you stop and say that the graph has no Hamiltonian cycle. In general, a black component may consist of 1 or more intervals, but in the special case of T subgraph free graphs, the number of intervals must be at most 2, which is the longest claim to prove. In this particular example, we have a black component consisting of this, and this vertices with three intervals, which means that probably there must be a forbidden graph here somewhere, and it exists, of course. By the way, as a subgraph, this edge must be deleted to obtain a graph. So this graph is shown in both edges is a forbidden graph. Now, if your input graph has a black component in which contains a set of contact vertices of cardinality different from 2 or 4, you stop. So the number of contact vertices must be 2 or 4 and nothing else. What if your black component contains exactly 2 contact vertices? Then all vertices of this component must appear consecutively on the cycle. In which order? It doesn't matter, because only contact vertices have neighbors outside the component. So all you need to do is just to check whether your component, black component, contains a path connecting contact vertices. Path containing all vertices of this component and connecting them. Such a path may exist, may not, but the component is small. It's bounded number of vertices. We can easily check. So all black components have bounded size. And if such a path exists, you take it, delete all edges except the edges in the path, which makes all vertices white. If such a path does not exist, you stop and say there is no Hamiltonian sum. Now let's look at a black component with 4 contact vertices. If a cycle, a Hamiltonian cycle exists, then we must be able to partition the vertices of this black component into 2 parts, or 2 paths, connecting vertices somehow. Let's say something like this, connecting this vertex to this and this to this. I call this pairing. A pairing, again, may exist, may not, and if a black component with 4 contact vertices does not admit any pairing, then you stop. The graph has no Hamiltonian sum. If at least one pairing exists, then you check whether you can find pairings of different type. By different type, I mean maybe all pairings connect this vertex to this and this to this. In different ways, but only this to this and this to this. Then you, in the Hamiltonian cycle, there must be an interval containing this, connecting these 2 vertices, and an interval connecting these 2 vertices. And again, it doesn't matter which of the pairings you choose, because only contact vertices have white neighbors. So what you do here, you choose arbitrarily any such pairing and delete all edges from K except the edges in this pairing. This may disconnect the graph, but then you stop and say there is no Hamiltonian sum. Finally, what if we can find pairings of at least 2 different types? For instance, oops. For instance, like this and like this. Now you model this situation by replacing your black component with a square. And if each black component in your graph is a square, a graph in sigma 4, then I claim that the cycle necessarily exists. When I came to this conclusion, at some point, I asked myself, what I need to do next? How can I determine whether the cycle, before I knew that the cycle necessarily exists, I wanted to decide, how can I decide the existence of the cycle in this case? Then I realized that the argument is simple, and the argument is this. To construct a graph, we must delete either these 2 edges or these 2 edges from each square, from each black component. And we must delete 2 edges from each black component, from each square, in such a way that the resulting graph is connected. That's it. That's all we need to do. And I claim we can always find such a couple of edges, such that the removal of these 2 edges does not disconnect the graph. Why? Assume to the contrary that by deleting these 2 edges, we disconnect the graph. There are no edges between these 2 edges. And by deleting these 2 edges, we again disconnect the graph. There are no edges between this part and this part. Then, by deleting all 4 edges, we obtain 4 subgraphs. In each of them, this vertex becomes vertex of degree 1, because 2 edges have been deleted. What can we say about any other vertex of 4th degree, if it exists somewhere? It belongs to a square, and every square contains evenly 4. for vertices of odd degree, which means that in this part we have an odd number of vertices of odd degree, which is not possible. That's why either in this way we do not disconnect the graph, or in this way we do not disconnect the graph. Okay, now a couple of more open problems. So remember that when we excluded a tripod forest, we excluded a graph, every connected component of which is a tripod. But when we talked about this guy, we excluded just this guy, connected one graph, a graph with one connected component. What happens if we exclude a graph? Every connected component has this form. I don't know. I don't yet know. Can this result be extended to the case where every connected component is of the forbidden graph is isomorphic to Fk? I believe that in this case somehow the problem is still solvable. Also, when we talked about this graph Fk, then we didn't care about the length of the hairs of the branches. For each value of k, we have a solution. Here we have to be careful, because if we extend this guy a little bit here, here, and here, we obtain a graph where the problem isn't complete. So can the last two results, this one and this one, by the way, for this result, for the polynomial time solution for when we exclude this guy, the approach is completely different. It is based on the analysis of long chords, and there is a definition of long. In this case it's 7 or something, I don't remember. And the thing is that in this class, long chords, if the cycle exists, long chords do not cross each other, which allows to reduce the problem again to sigma 4. Again to sigma 4. Now, can the last two results be extended to connected forbidden graphs with longer hairs? It's still an open question. I tried to extend these hairs a little bit and apply the arguments developed for non-crossing long chords, and this argument doesn't work if we extend this guy a little bit. And finally, what's the complexity of the problem in sigma 6? Very interesting question. And a couple of more comments. So, returning to the very beginning of my talk, I identified a number of critical monotone classes. Here I also put the unknown class X, or maybe it's a collection of classes X, which are critical for the Hamiltonian cycle problem, still an open problem. But as I mentioned earlier, you can identify many other critical classes, not necessarily comparable with this. This sequence of classes is a chain. For instance, I know that the class of star forests is critical. In what sense? For instance, with respect to the so-called H index. H index is the maximum value of k, such that the graph contains k vertices of degree at least k. In the class forest, this parameter is unbounded. You can find arbitrarily many vertices of arbitrarily large degree. And this is a minimal hereditary class where the H index is unbounded. In a recent paper with a number of co-authors, they identified all minimal classes of unbounded H index in the family of all hereditary classes. And by projecting this result to the case of monotone classes, we conclude that the class of star force is the unique minimal monotone class of graphs of unbounded H index. It would be nice to support the importance of this class by identifying some algorithmic problems for which this class is critical. And I believe that there is such a problem, so-called achromatic number. Hans Badlander, in this paper, written many years ago, proved that computing the achromatic number is NP-complete in a certain class of graphs which is a slight extension of the star forest. In his construction, each connected component of the graph is a star, except one component, which is two clicks joining a single vertex. And I'm confident that this strange component can be somehow eliminated and the problem can be reduced. It's possible to show that the problem is NP-complete in the class of star forests. It's a conjecture. Final conjecture of my paper. Thank you very much for your attention.
Thank you. Questions?
Sorry, what is achromatic number?
Of what?
What is achromatic number? In
Achromatic number. Ah, you want a definition?
Yeah.
Does anybody remember? Okay,
Isn't
it's
there any union of two color classes?
no. It's
forest?
you partition a graph into independent sets. You want the number of independent sets to be as large as possible, but you want at least one edge between any two color classes.
And this one edge.
So it's the maximum number of color classes or independent sets with the additional assumption that between any two color classes there exists at least one edge. Of course you can put, in general, if you don't assume that there is an edge between two color classes, you can put a single vertex in each color class, but it's not, we want, for instance, achromatic number is unbounded in, I mean, not computing difficult, but unbounded in graphs of this type. Because if you have k edges like this, you split the vertices in k, choose two subsets, and put an edge somehow between them. So for each pair of subsets, you put an edge. So the chromatic number, a chromatic number, is unbounded and it's simple. And computing a chromatic number is a very difficult. Problem. Why don't you ask what is this picture? I made it here in Daejeon recently, a couple of days ago. I was working in the evening, and in one of the it was on Saturday, if I remember well. And in one of the buildings, they projected this picture. They made it very. It was on the ceiling.
Oh.
So I thought graphs are everywhere. we live in the world of graphs.
It's a star forest with cycles.
Are there any other problems other than Hamiltonian cycle where you also have some classifications like this?
For the last half of 6 or maybe more than 6 months, I was working on the Hamiltonian cycle problem, so I'm occupied with this problem. But of course, there are lots of. You mean algorithmic problems? Are you interested more in algorithmic problems? In the last couple of decades, I work mostly on structural problems. Algorithmic problems are not very interesting. Calculating is a boring thing.
I mean, for graph coloring, there's such a, like, we know pretty exactly what graph, if you just forbid a single graph, what
Yes.
Yeah. There is a nice progress towards the only boundary class for the independent set problem. It's the class of tripod forests. It is known that this is the, I mean, this is a limit class, and for a long time, people try to prove that this is the only limit class. This is the boundary class, meaning that you forbid a graph. You forbid a tripod forest as an induced subgraph. For the monotone class, everything is clear. I mean, if you don't forbid a tripod forest in the family of monotone classes, it's an NP-complete problem. If you forbid a tripod forest, it's bounded tree width and polynomial times solvable. But for the family of hereditary classes, It's still open, but people make great progress. And if I remember well, for bounded degree graphs, it's already proved. If you forbid a tripod forest as an induced subgraph, and you assume bounded degree, then the problem is polynomial time solvable. And probably somebody also proved that found sub-exponential algorithms if you forbid tripod forest as an induced subgraph.
For H4 and H5, can you reduce it to sigma 6?
Yes, this is what I have already a reduction to sigma 6 for H4 and H5 subgraph free graphs. It's a even longer reduction.
Okay, I was going to ask how complicated
it's
it is.
it's a longer reduction. But
Okay.
and the obstacle is C6. Without knowing how to solve the problem for sigma 6, because by forbidding H4 or H5, we do not destroy this class. So we either able to solve the problem. It's the problem is NP complete for sigma 6. It's NP complete for H4 and H5. It's if it's polynomial time solvable for sigma 6. It's polynomial time solvable for H4 and H5.
Any other questions?
If we all of the only one or two black component which has 6 cycle in the sigma 6, then is it Hamiltonian?
Look, I'm an old man. You need to speak
So-
very loud to me.
If we all only in the sigma 6 class, if we only all the one or two component which has 6 cycle, then does it?
Probably, yeah. If the number of 6 cycles is bounded, most likely, definitely we can solve it.
You can try all possibilities, right? Yeah.
There's only a constant number, so you can just try more.
And what I mean is we have possibly more 4 cycles.
Yeah, but what you could do is just like make several copies of the graph, guess the matchings for the 6 cycles, and just look, because those are now sigma 4 graphs. If they're still
Right.
connected, you're done.
So you only have you can reduce to problem one sigma 4.
Yeah.
Right. So maybe we should conclude today's talk. Let's thank the speaker.